Okay, so I want to talk to you about the band theory of solids and how that can explain um, three types of materials: conductors, metals usually, insulators, and semiconductors. So before we start on that, I'm assuming that you know um, molecular orbitals in chemistry. Okay, molecular orbitals. If you don't, you can just go to Khan Academy or somewhere. But basically, it's got this S shells, P, D, F. They're actually quantum um, numbers and so on associated with these different orbitals. But hydrogen, for example, is electronic orbital is 1s1 for neutral hydrogen. Helium is 1s2, and then lithium is 1s2, 2s1, etc., etc. You got three electrons. I won't go through that now, right? But let's look at what happens when you have one lithium. So let's say you have one lithium, and then just plot it over against energy here on the y-axis. Excuse me, energy. And when you do this, let's say you have, lithium is 1s1, sorry, 1s2, 2s1, right? Three electrons, yeah, neutral lithium. Let's look at the valence electrons only. So don't worry about the internal one, just the valence one. So with valence one, you've got one electron in the outer shell, the 2s shell, right? The 2s shell. Let's say you only have, in the case of lithium, just that state. That's one lithium. If you have many lithiums, then it splits into two levels. So one level is called what they call the anti-bonding. Anti-bonding. It's a higher energy, so it's less likely than the bonding one. So this is the bonding one over here. So this is lower energy, therefore it is the bottom one is more likely, the top one is less likely. How did you get that? Well, there's a smart guy named Schrodinger, Schrodinger, who came up with the Schrodinger wave equation, and he basically came up with the description how electrons can be represented as a wave function. Remember, everything has a wave, including your body, but our body has too much mass to have you know a reasonable wavelength, whilst electron has so small a mass, it can have a big wavelength. Yeah. So we are waves. Electrons are waves also. So Schrodinger says that when you have electrons, valence electrons including, you have this wave equation, what they call psi, right? And when you have more than one lithium, and you have two lithiums, for example, let's draw it here, lithium and lithium, then the valence electrons kind of the waves combine with each other, and there are two potential states. One is constructive interference, you can call it. One is destructive, and the constructive one is kind of the two wave functions plus each other. So that's kind of the bonding state. So it's a wave function, so it's a linear combination of these equations. One is the plus function, you can call it constructive interference, lower energy, so it's more likely to happen. And the other one is the destructive interference, so you can do it this way. Let's call the A21 higher than the A1, so you can make it look like that, for example. So that's the anti-bonding, so it looks at the top. So that's how the equations are organized. Now that's just with two lithium. What if you have many lithiums, specifically 6.023 times 10 to the 23 lithium, 23 lithium, or Avogadro numbers worth of lithium, right? 1 mole. When you have 1 mole of lithium, then this splits into so many little bands. That's another band there, another level there. So and this one here has another one, another one, another one, another one. So there are lots of bands, which adds up to you know we can split into that, right? Adds up to Avogadro numbers and levels. Yeah. And when this happens, How can that happen, Mr. Tree? Well, when you have the bottom one, for example, let's say 6.023 times 10 to the 23 atoms, this one here is kind of the lowest possibility of linear combination. So everything is positive, 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 constructive interference, etc. Positive, positive, positive. Fantastic. This one is positive. Oh, sorry. This one here, excuse me. The top one is negative, 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 right? All destructive interference. Actually, I'm wrong. This is positive, negative, positive, negative. Yeah, positive, negative. Over here, you don't need to know the details. This is just approximate. Positive, negative. Yeah, and then the second lowest level, it could be mostly positive. And then there's one negative there. So um, maybe a couple of negatives there. So that's one level, etc. A little bit higher energy or less likely is another one, etc. So all these combinations happen, and they can't occur at the same energy level. So there is a rule called the Hans rule. You'll know this from chemistry. The Hans rule states that every level has to be unique. Every energy level has to be unique, so they can't occupy the same energy levels. Each electron cannot occupy the same energy level, so there's these unique levels where each electron can go in. So in the case of lithium, when you have many lithiums, Na times of lithium atoms, then you know that one lithium only has one valence electrons. So in the case of two lithiums, because one orbital can take two electrons, one up, one down, right? So basically, when you have two lithiums, one, both of them are at the bottom and the top one is empty. Yep. When you have 6.023 lithiums, again, this is up and down, up and down, up and down. So basically, you'll discover that half of this will be filled. So half filled. Yep, with all the 2s1 electrons in there, and the other half is not filled. So that's an example of lithium, which is a conductor. Yep. So let's look at let's look at another metal. For example, let's look at copper. In the case of copper, you have, this is the electronic configuration of copper: argon 3d10 and 4s1. Again, in the case of copper, you have 4s1 orbitals, and when you have Avogadro's number with orbitals, yep, this will split into so many levels, linear combinations of Schrodinger equation. Excuse me, etc., etc., etc. Sorry, the drawing is not as easy on this as the whiteboard, as you know. And these are basically all the S bands, all the S bands here. And again, only half of this will be filled, half filled. And you can try it yourself by having two copper, three copper, and so on. So you have, one up, one down. The next one up, one down. Yeah, one up, one down. And then you'll basically only occupy up to here. Yep, it doesn't go up there. So because it occupies the lowest energies first. All right. So the top one's empty. So as you can see, the bands are combined together. So this is a typical characteristic of a conductor. So this is type 1. In terms of electrical conductivity, you have three types of materials. Yep. This one, excuse me, all materials. Sorry, Avogadro number, orbitals. This is copper we're talking about. Yep. Two types of materials. One is the conductors. Another one is insulators. And another one is semiconductors. When you have conductors, then as you can see there, you have all these one band combined together. It's half filled bands, half filled bands. It can be half filled S bands or half filled SP bands, orbital. But basically, this is empty. So they kind of combine together what they call conduction band. Let's talk about insulators first, so it's easier. In the case of insulator, it splits into two. It's got conduction band, what they call conduction band, empty. It's empty, right? And all the field, what they call the valence band. And the distance very far. It's more than 3 mega electron volt. Sorry, it's 3 electron volt. Yep. And in the case of metals, the conduction band and the insulators, the valence bands are the same. So they're overlapping. So both conduction and the valence band overlap. So basically, these valence electrons here can just travel there very quickly, and it conducts to the next metal. That's why metals have this sea of delocalized electrons, right? Electrons can go left and right. Well, in the case of the electrons here in the insulators, they can't go up to the conduction band, so it doesn't conduct. It's kind of locked in, and the energy gap is too far to jump up. Semiconductors are special type of materials where, sort of in the fourth group in the periodic table, where the valence band is at the bottom here, and the conduction band is over here. Yeah, empty. Yeah, initially empty, and you have this gap, and the band gap they call it, which is only less than 3 electron volt. So silicon is about 1.1 electron volt. So even thermal energy can make some of the electrons jump up. Great, and it becomes conductive, right? Some of the electrons can jump up with thermal conductivity. So hopefully you understand a little bit of that. So I'll just move to the next one. And how did this happen with regards to semiconductors and metals? So I just want to present to you something called the energy, but also a separation distance here between atoms. Separation distance between atoms. And then you have 3s here, 3p, for example. This is the orbitals, and as the atoms get closer and closer together, there are more of them overlapping, right? Overlapping, and therefore different states of quantum states. As I said before, different quantum states, half filled. Similarly, the 3p is the same. It splits into different quantum states as more and more atoms get mashed together. The two atoms get mashed together. The quantum states, they get filled in together, half filled in as well, until there's an overlap here. The overlap starts to happen, and we talked about the overlap just then. And when this happened, this is the different levels, right? And as everything gets closer and closer together, some of the S and P can join together to form sp3 hybrids. sp3 hybrids. You can check your chemistry notebooks from high school if you forgot what it is. So basically, it splits again somewhere here into the what they call the valence band. Valence band probably doesn't look that good, so I make it this way, and the other one splits over there. Right, so something like this, conduction band, with the most of the electrons filled in here, and this is the conduction band. So it probably doesn't look that good, but something like this, right? And if you do the measuring, this is all the energy levels. Yeah. Sodium, for example, is the distance is between atoms is around 0.37 nanometers, and sodium is clearly metal. So basically, the conduction and the valence band are introduced there, and it's only half filled with electrons. We already talked about it, so it's a conductor, right? Well, so if you have a silicon, which is somewhere here, a silicon will have a separation distance of 0.222 nanometers, which is smaller than this. So as you can see, it's got a small band gap of 1.1 electron volt, and therefore that creates this situation where for silicon, the valence band, the conduction band, and the gap between that and the valence band is very small, 1.1 electron volt. Right? For a metal, it's kind of combined in a conductor. It's kind of meshed together. Okay, it's combined together. This is conductor, and this is a semiconductor. And then for an insulator, the distance is very far. All right, the distance is very far, kind of typically represented by this between the and this is greater than 3 electron volts within the valence band and the conduction band. Okay, so I hope that makes sense so far. So that's the three types of materials. Okay, let's talk about what is this split into two, the sp3 hybrids. Well, you know, the bottom half again is the bonding, you know, the linear combination of bonding orbitals, and the top one is another linear combination of the anti-bonding orbitals. So it's again Schrodinger equation. Okay, let's lastly talk about conduction. So the formula for conduction is conduction can be thought of as this is equal to the number of electrons times the charge of electron times what they call the mobility of electron, right? In this case, and if you increase the for metals, if you increase the temperature, for example, if you have electron field there, you know, electric field, so a positive and negative there, and then you've got all the nuclei over here, and the electrons are the sea of delocalized electrons there, and you increase the electric field, then the electrons will try, instead of going there, it'll try to go there, right? However, as you increase the electric field, it hits other nuclei and gets bounced off. So there are frictions, you know, there are frictions, hits atoms, and it reaches what they call terminal velocity. Yeah, terminal velocity, like if you're dropping off a parachute. And this friction, so this is called the friction, creates heat. That's why when you put electricity in metals, it gets hot, right? Because the electrons get, you know, hitting these things. So as a result, the mobility of the electrons with temperature, the mobility of the electron drops. If you increase the temperature, the electron jiggles a lot more, hits all the nuclei more, the mobility drops, right? Which means if this drops, then the conductivity drops as well, because that's the equation here. Okay, so that's for metals, you know, for metals. Now for the case of insulators, then the conductivity is equal to, depends on whether it's a p semiconductor or an n semiconductor, but let's call it the n semiconductor at the moment. Then it looks something like this: mobility of electrons. It can also be or the mobility of the p times the charge of electron, mobility of the p. Yep. For sorry, that's not insulators. That's semiconductors. And what happens here when you increase temperature is that also both of the mobilities also drops, similar to metals here. Yep. However, the number of electrons or number of holes left behind, number of electrons jumping up, the number of electrons increases significantly with temperature. That's the Arrhenius equation. So the number of electrons goes up, or the number of, in the case of p semiconductor, goes up. This is the n semiconductor, p semiconductor, goes up as a result, and this goes up a lot more than the reduction in the mobilities. Therefore, as a result, the conductivity actually goes up because of the most of these electrons jumping to the band gaps and going to the positive terminal. Similarly, the holes in the bottom go to the negative terminals. Okay, so the conductivity goes up if the temperature goes up in a semiconductor. Well, say the conductivity goes down when temperature goes up for metals, because the number of electrons is the same for metal. It doesn't, it's sort of there's no gap, right? So the electrons free flowing, sea of delocalized electrons in the valence shell. So this one doesn't change with temperature, whilst the mobility changes. Whilst in the case of semiconductors, the Ne or the Np goes up. Okay, maybe I should put this Np. Okay, so hopefully this helps, and see you next time.